In this video, we're going to take a look at Lewis structures. Now, a Lewis structure, we've seen Lewis dot diagrams in the past, and a Lewis dot diagram illustrates an atom's valence electrons by putting dots around it to represent each valence electron. Remember that bonding occurs to make elements stable, right? We want to fill their octets by making bonds through sharing electrons. So we can use Lewis dot diagrams to help us look at the structure of a molecule, how these atoms are bonded together, and we call these Lewis structures. So in your Lewis structure, you're going to see all the valence electrons. That's very important. So we're going to get all valence electrons shown. And you're either going to see them as what we call lone pairs, where they're just two dots together, or you're going to see them as bonded shared pairs. Now, bonded shared pairs are ones that are actually making up the bond. So these ones are usually going to be represented as a line in your Lewis structure. Okay. So to do this, the best way to start off is first to figure out, using your periodic table, how many valence electrons an atom might have. So let's work with our example of chlorine. Chlorine, if you look on your periodic table, chlorine can have 7 valence electrons. Okay, so since there's 2 chlorines, I've got 7 more. So when I add that together, I have a total of 14 electrons that need to be in this picture. So if we start with our Lewis structure of chlorine, if you remember, with its 7 valence electrons, you're going to see that we start to pair them up after we place 4 around that particular atom. And so that chlorine, that one chlorine, has one unpaired, and that's the one that's going to get shared between it and another chlorine. So if we draw in our other chlorine, we can identify which one's going to end up being the bonded pair, and that's going to be this set right here. And instead of drawing them as dots, what we'll do then is we'll actually draw it as a line. So the bonded set of electrons becomes a line in our Lewis structure, and these lone pairs that we have that aren't involved in bonding are still shown. And if we count our structure, we'll have used all 14 electrons. So we've got 2, 4, 6, 8, 10, 12, 14. So there's 14 electrons around the chlorine and the chlorine, right, around that Cl2. So we've got our Lewis structure for Cl2. Right, let's check out another example, C2H6. So again, think about your number of valence electrons, and off to the side, so I'll just do it here. Carbon's going to give me 4 valence electrons. So I'm just going to put 4 electrons. And because remember, it's in column 14, and anything in column 14's got 4 valence electrons. Hydrogen in column 1, hydrogen is only going to have 1 valence electron. Now, the thing we have to remember is that there are 2 carbons here, so I'm going to multiply by 2. So that means I'm really dealing with 8 electrons coming from my carbons. And I've got 6 hydrogens, so I'm really dealing with 6 electrons from the hydrogen. So that's a total in this picture of 14 electrons we need to have. Now, when doing Lewis structures, it's always good to put our central atom as the atom that has the greatest bonding capacity. So the one that can make the most bonds, we usually want to have in the center of our molecule that we're drawing. And if you've got multiple atoms that have lots of bonds available, like in this structure here, we've got 2 carbons, then start to look at some symmetry. Start by placing 2 carbons directly in the middle of our structure, okay? And we know that no matter what, we can have them, they have to be bonded together at least once. And then we can look at putting our hydrogens around. So now we've got those carbons bonded. Now I want to make sure I bond each hydrogen. So I'm going to bond each hydrogen, which remember the bond is representing a pair of electrons. And I've used 3 of them so far, and I've filled up the bonding capacity of carbon, because carbon can only make 4 bonds, because if you remember, right, with its 4 valence electrons, that leaves 4 spaces to share an electron with. So that first carbon's got all the bonds it can make, and I'm going to go to the second carbon, and then I'm going to put the rest of my hydrogens on my molecule. Right? So at this point now, I've got my hydrogens thinking they've got their 2 electrons, and that's all they need to fill their shell. The carbon thinks it has 8, because with 1 bond, a second bond, a third bond, and a fourth bond, right, each bond representing 2 electrons, it thinks it has 8 electrons. So in this picture, hopefully I've used all 14 electrons. So if I'm going to count my electrons here, I've got 2, 4, 6, 8, 10, 12, 14. So I've used all 14 electrons, so I've used them all. I don't have any left over. My structure's done. So that would be my Lewis structure for C2H6. If for some reason you get a structure where you have some left over and you've met the bonding capacity of everything, then this might be a weird, like, exceptional type case where you might then take those leftover electrons and put them around the central atom is typically what you do. So you'll only see this a lot of the time when you start to get into more inorganic molecules, like scenarios where you might have like bromine at the center of a molecule or something. But when we're dealing with our organic chemistry, you're going to see that that's not the case. Carbon's going to make its bonds, and you're going to be good to go. All right, our last example, C2H4. So again, I'm going to kind of keep track off to the side. My carbon's going to have 4 valence electrons, but there's 2 of them. So I've got 8 electrons coming from my carbon. And my hydrogens, 1 electron with each hydrogen, but I've got 4 of them, so that's 4 valence electrons. And that means in this picture, there needs to be 12 electrons. So we've got a different number of electrons here. Let's see what we can do. Again, I'm going to start with carbon in the middle, and I'm going to bond 1 carbon to the other. Right, so I've now, out of my 12 electrons, I'm just going to keep track. Out of my 12 electrons, I have used 2 of them by making that bond. So I have 10 left to go in my picture. This is where now I start to look at some symmetry, okay? So as we start to look at molecules, you'll notice that molecules tend to have symmetry associated with them, naturally. So instead of completely filling with 3 bonded hydrogens to 1 carbon, we're going to start by, let's put a hydrogen onto each carbon. And then let's put a second hydrogen onto each carbon. So now I've got my 4 hydrogens. I just used 2, 4, 6, 8 more electrons. So that leaves me with 2 electrons left, right? So after making all those bonds, I have 2 electrons left, but I don't have any more atoms to put on. So this is a scenario where I'm probably going to have to increase the number of bonds, or there's going to be a lone pair somewhere. So if I look at my atoms, my hydrogens, they've made their 1 bond, so they're happy. But my carbons only have 3 bonds. And remember, they want to make 4 bonds. By having 4 bonds, that'll be 8 electrons around them to fill their octet. Right now, this carbon only thinks it has 6, so it needs 2 more electrons. So if I were to take my lone pair and put it there, that uses my 2 electrons. I don't have any more, and the problem would be this other carbon is still missing electrons, right? It only has 6. It wants to have 8. It needs to have 8 around it, an octet. So what we need to do then, instead of putting that last 2 electrons as a lone pair, let's put it as a shared pair between the carbons. Right? So once we put it as a shared pair between the carbons, as another bond, right? Now we've made what's called a double bond because there's 2 bonds between the 2 carbons. By sharing that last 2 electrons, we've used them all in our picture. So we don't have any left, which is awesome. And we have all 12 in here. So we've got 2, 4, 6, 8, 10, 12 electrons. So that's good. And now everybody's met their octet requirement. Hydrogen's got its 2 like it normally needs in each scenario because it's got its bond. And carbon, each carbon now thinks it has 8 because each bond is sharing 2 and each carbon has 4 bonds. So this is an example of some Lewis structures, and good luck practicing with your Lewis structures.